And moving on to chapter 17. Okay, what we did in chapter 16 in calculating pHs and things is we looked at pH of, say, just acetic acid or the pH of just ammonium nitrate. There was only a single solute in the solution. But in this section, we're going to start with when there's two solutes in solution. For example, in chapter 16, if we were going to calculate the pH of 0.1 molar acetic acid, then how we started that is, y'all will remember, we set up an ice table. And we said, well, we start with 0.1 of this. The water's not going to matter. We're not going to start with any of this. And every time we ended up with Ka is equal to x squared divided by the initial concentration minus x. Okay? So I think we've got that pretty down pat in doing those calculations. But what if we had to calculate the pH of a solution that was 0.1 molar acetic acid, and let's say it was also, it had 0.05 molar sodium acetate. There's a common ion. What is the common ion between acetic acid and sodium acetate? Because we're still looking at this reaction for what's going on. Clearly, the common ion is the acetate. So what that means is we're not starting with 0 acetate. Now, we're also starting with 0.05 molar acetate. The hydronium ion is still 0. Okay, we could go back, and your book will go back and explain how to go back to this, except it's not x squared now. It's going to be the acetate and the hydronium ion, okay, divided by the acetic acid. But a simpler way to do it is to recognize that this is a buffer. What is a buffer? Y'all might have heard of buffer systems in biology or A&P. A buffer is a solution that resists a change in pH. Okay, buffers are systems that help maintain the pH. Different systems processes have to happen at certain pHs. If you guys treat your own swimming pool at home, you add buffers to that. You have to maintain the pH of the water, and you add things to help it maintain the pH. Biologically, your blood is buffered. The pH of blood is 7.4. And it's very important that your blood pH stay at 7.4. It's a bicarbonate system that buffers your blood. And so certain traumas, certain medicines, certain sicknesses, certain things going wrong in your body can cause that pH to change, but your blood is buffered to try to maintain it close to 7.4. And it doesn't, as far as your body goes, you don't have to get very far from 7.4, and medical professionals, there's nothing they can do. Once your blood drops, I'm not sure what the critical level is. I'm going to say maybe 6.9. But the blood can't recover from that. But that's what a buffer system is. It just resists a change in pH. And so how you make a buffer, if you have a weak acid and its conjugate base, that makes a buffer. That's what we have here in this example. We've got a weak acid and its conjugate base present. Okay. Another way to make a buffer is with a weak base and its conjugate acid. And that's the only two ways we're going to examine right now, is making buffers with weak stuff. And so the reason these are buffer systems, the reason they resist a change in pH, it's because they're equilibrium processes. And it goes back to Le Chatelier's principle from chapter 15. If you'll remember, Le Chatelier's principle said if you have a system at equilibrium and you apply a stress to the system would respond to relieve the stress. And so, like, if we were just looking at this in terms of Le Chatelier, guys, do you see that if you added acid to the system, so you're overloading the product side, this system is going to respond by shifting to the left, or we would say to the reactant side. The reason a buffer system can do that is because you have some acetate there that can neutralize some of that acid that you might have added. Okay? Likewise, on the flip side of that, if we added base to the system, if we added something that would increase the pH, like hydroxides, the hydroxides would combine with the hydronium ions, removing those. Okay? It's like pulling this out of the system. When you pull that out of the system would respond by making more. Okay? So the hydronium ions that are there would neutralize the hydroxides, but the system responds by shifting this way to replenish the hydronium ions you removed. And that's how the buffer works. Okay, and we'll talk more about that as we work some problems. But let's look at how we calculate the pH of a buffer. There's a nifty little formula, and it's called the Henderson-Hasselbalch equation. Some of y'all will go on to take biochemistry. And when you take biochemistry, you will certainly use the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation looks like this. The pH is equal to the pKa plus the log of the concentration of the base divided by the concentration of the acid. Okay? pKa is a new something that we have to do. To get the pKa, that is simply the negative log of the Ka. And just for future reference, that's what that little P in front of stuff means. P in front of stuff means that you need to take the negative log of it. For example, what is pH? It's the negative log of the H. POH, negative log of the OH. Okay, so if you forget, maybe that'll help you remember. So, for the problem we just looked at, if we want to calculate the pH of a solution that is 0.10 molar acetic acid and 0.050 molar sodium acetate. Okay? So, the pKa, we're going to look up the Ka for acetic acid. The Ka for acetic acid is 1.8 times 10 to the minus 5. The negative log of that, I think it's 4.74. So the pKa is 4.74 plus the log. The base is the sodium acetate. So the concentration of the base is 0.050. And the concentration of the acid is easily acetic acid. Okay, so the pH of this is going to be 4.44. That's the pH of the buffer solution. Now, let's add a second part to this. let's calculate the pH after adding 0.01 moles of a strong acid. And we are going to assume the volume remains constant. Okay, to explain that, I'm going to go back to the previous slide because I explained it before, but now we're explaining it with actual numbers. Okay, this is an acetic acid sodium acetate buffer. This equation shows this buffered reaction. In the problem I just gave you, I told you we're going to add some of this. We're adding strong acid, so we're adding hydronium ion. According to Le Chatelier, which direction is this going to shift? It should shift to the left if we add strong acid. If we add something over here, it shifts left. If we add something over here, it would shift right. Okay? So if it shifts to the left, that means whatever we added, we're going to have to subtract from the base, and we're going to have to add it to the acid. That's what's going to have to happen for it to shift left. So we're going to subtract it from the base, which is on top, 0.01, and we're going to add it to the acid, which is on the bottom, 0.01. And I'm going to go to the next slide. That means that the pH, this is still the Henderson Hasselbalch equation, is equal to 4.74 plus the log of the base concentration is now 0.04 and the acid concentration is now 0.11. And the pH is now 4.30, which, look at your numbers, does that make sense? If we go back to the previous one, we started at 4.4. We add acid. Now, a buffer resists a change in pH, okay? It doesn't guarantee there's no change. It just changes a small amount. If we add acid, we expect the pH to go down, and it did go down, but it only went down a small amount. Okay, to put that into perspective, if we had, if we had just 0.01 molar strong acid, the pH of 0.01 molar strong acid, the pH would be 2. So the fact that this only dropped by, 0.13, 0.14 pH units is something, because the pH of just that strong acid by itself is 2. So this is a buffered system. Okay? And how that would change here, like if you added strong base, you would then add to the base and subtract from the acid. Okay? So that's a good start to chapter 17. And that'll take care of the first two sections in chapter 17, 17.1 and 17.2. And in the next lecture, we'll look at titration calculations.